All right, well, so any questions before we continue forward with review? So I think we were up to trees. So binary search trees, you've done a bunch of stuff with BSTs, right? So mostly recursive algorithms other than breadth first traversal. But
the only thing unique about breadth first traversal is that it uses a queue.
Yes, and it uses a loop usually inside. Other things like search, insert, we can do those with loops or we can do them recursively. And we usually do them recursively because it's less coding. So depth of a node is the number of links from the root to the node. Height of a tree is the depth of the deepest node. Null tree has a height of -1, right? Make sure you remember that because everything else is relative. Make sure you know with a definition of a balanced tree. So what does a tree need to do in order to be balanced? What are the 3 properties it has to satisfy?
Height of left and height of right are less than 1 apart.
Yeah,
Right.
difference in height is less than 1.
Difference in height is less than or equal to 1.
And preferably that you fill every level first before you move on to the next level.
Not necessarily.
Both sides.
For a heap, that's true.
Both sides of the tree need to be balanced.
Right, both sides need to be balanced, which almost is the same thing as what you said. So balance is a recursive definition. The heights have to be within 1, and the left subtree and right subtree have to be balanced themselves. If all 3 of those things are true, then the original tree itself is balanced. In deletion, the way we delete typically, we take the largest thing from the left subtree or the smallest thing from the right subtree and use that to replace the root. If you're not deleting the root, delete is recursive. Right? Find the node you want to delete the root of that subtree, and leave everything else in the tree alone. So AVL trees are binary search trees that are balanced, right? So satisfying that balance requirement. And to work with AVL trees, we usually do the following things. One, we have to compute a balance factor for each node. So you remember what the balance factor of a node is?
AVL stands for what again?
Let's look it up because it's 3 people's names. Well, it's two people's names, but one person has 2 names. It's Adelson and something. Adelson, Velsky, and Landis. But Adelson gets 2 initials. So what's the balance factor of a node?
So the difference between it's left and right.
Yes, it's the difference in height between the left subtree and the right subtree. So that's just a straight calculation. And if the tree is balanced, every balance factor should be 0, 1, or -1. If the tree is unbalanced, there'll be a balance factor of 2 or -2. And if it was balanced to begin with, when you insert a node, it might become unbalanced, and that's where this table comes into play. So starting with a node you insert, you move up the tree, you look for a balance factor of 2 or -2. If you find a balance factor of 2, for example, you would look to the node on the left and see if its balance factor is 1, 0, or -1. That tells you which of these cases you're in. And then whichever case you're in, you basically make an adjustment so your tree looks like this and changes into that, and then changes into the balanced case. And these rotations, these adjustments, preserve the search order of the tree. So for example, everything in A is smaller than 3, so A is always to the left of node 3. But when you finish coming down here to this bottom row, your balance factors are guaranteed to be 0, 1, or -1 everywhere.
and heights? Or?
Yeah, so it's the height of the left subtree minus the height of the right subtree. If you get that backwards, then none of these work because they'll be the negative of what they should be. Yeah?
So, for a question on the test, for example, would you go like, have a tree and then try to balance it?
Mm-hmm. Yeah. So I won't ask you to write code to do AVL balancing on the test, but I might give you a tree and ask you to calculate balance factors and ask you to do rotations on it on paper.
And you said we could use that sheet.
Yeah, so I'm going to pass out one of these with the exam to each person, so you don't have to make a copy of it, and it doesn't count against your page budget, so you still get 8 pages of your own notes. But you also got this. So you got 9 pages. All right, so that's really the gist of AVL trees, right? Figure a balance factor, do these rotations to restore a balance. And we did this on the board. We did it for inserting, so I'm not going to ask you about deleting, but it's basically the same thing when you delete. Tries. So tries are like these really wide trees where you have nodes associated with each letter, or whatever your string is made of. So it's this kind of thing, right? So this would be a try node, and when you want to add a word, for example, for each letter of the word, you have the corresponding letter in this node point to another node, right? And after your last letter points to another node, you set the end of string flag to be a 1. Right, so you've done this on the board. If you didn't do this, ask lots of questions right now. But basically, so if this was the root of our try, right, we could have different words stored in here, and you can find the words that are in there by just following the links, letter by letter. You can store words by following the links, and if you want to add a word that begins with L and L points down here, then you move down here and you look for the second letter of your word, and if the second letter is an O and O doesn't point anywhere, then that has to point to somewhere new. So normally these are all null and end of string is 0. When you need to point somewhere, create a new node and point to that.
So a try is basically a structure of pointers to foo itself.
Yeah, and it's kind of like this would be like a 26-way tree. So each node has up to 26 children. And as you move down from parent to child, you're going through the letters of your word. And then there's just this end of string flag to say you reached the leaf. So tries want you to know the basic concepts. I want you to be able to work with pictures like this, right, and make changes to it or analyze them. Dynamic programming, that's what you were doing for 215, for PA5. Right, so knapsack, rod cutting were 2 main examples. So dynamic programming, we have a recursive function. So we want to find the value of some function f at a value n, and it somehow involves evaluating f at smaller values than n, right? It may be n minus 1 or n minus 3, or it may vary from situation to situation. But basically, when you can write a function as an expression of other values of that function, that's a recursive definition, right? And it parallels the idea of recursion, where to calculate a function, you call that same function inside itself. And so if you want to write a factorial function, right, right? There's a typical case. So fact of n says if n equals 1, just return 1. Otherwise, return n times fact of n minus 1. This right here is the recursive part, right? So it's calling itself. In this example, if we want to calculate fact of 5, we're going to have to calculate fact of 4, and fact of 3, and fact of 2, and fact of 1. And when we try to calculate fact of 1, it's just going to return right away. Once we calculate fact of 3 once, we're never going to try to recalculate that, right? We only need to calculate it once to multiply 4 times fact of 3 in order to find fact 4. So dynamic programming would not really buy us anything with a factorial function. But with knapsack, for example, when we try to find max val of 10, our code may end up calling max val of 4 a bunch of times. We might call it hundreds of times, right? That's a case where dynamic programming can come in and speed up the code. So that's where in the beginning of our recursive function, we check to see if we've already calculated that value. And if we have, we just read it out of memory. If not, we go ahead and do the recursion, but before we return, we save the value in an array so that next time we don't have to recalculate it. So that's what caching of results means, right? That's the essence of dynamic programming. So it comes into play when you have these recursive functions where you're going to need to calculate values of a function at smaller values, but also where you have this repeated substructure, right, where you keep calling those smaller function values again and again and again. That's where you want to throw them into memory. All right, so sorting. Bubble sort. You're good with bubble sort? Right, go through, swap things that are out of order. Every time you go through, the next largest thing sinks down to the bottom, the smaller things float up to the top.
I'm curious about how gravity sort works.
Oh, what?
How gravity sort works.
Is that, I don't know, gravity sort. Is it different from bubble sort?
I think so. It's kind of, I'm not entirely sure how it works.
That kind of sounds like a bubble sort in which the small things float to the top and heavier things go to the bottom.
Let me take a quick look. But if it's not immediately obvious.
Sort of, it doesn't seem to be doing nearly as many comparisons.
Oh, are you looking at a video of it? Explain like I'm 5. There we go. That works for me.
Okay. Also the count sort, but that one I actually don't understand what it's doing.
I do not understand.
Don't know off the top of my head. Tell you what, shoot me an email or post a question on Canvas and I'll dig into it later. There's a ton of sorting methods though in general. There's, you know, dozens, maybe hundreds of different types of sorts. And they all have different characteristics, different performance. Some of them work better or worse in certain particular situations, like if your data is sorted or badly sorted to begin with. But I don't think I'm familiar with a gravity sort.
Are all of these types of sorts going to be covered in the exam?
So these are all fair game, right? So bubble, insertion, selection, merge, heap, quicksort, radix sort. So let's run through those. So bubble sort, you're comfortable with. Selection and insertion sort, these are similar to each other. So let's do selection sort. So both of these, we have an input array and we have an output array. And selection sort, insert sort, they work by basically taking things from your input and copying them to your output. Okay, so they're both similar in that sense. The difference is basically where you're doing the work, where you're doing the sorting. So selection sort does the work when you select which things to move. Insertion sort will do the work when you decide where to insert what you're moving into the output. Okay, so let's just do selection sort first. So we select the smallest thing in our input that looks like a 2, and we copy it to the output. Now we select the smallest thing in the input that looks like a 4, copy it to the output. Select the smallest thing in the input, that's a 5, copy it to the output. Right, so the work is happening when we go through our input and we try to figure out what's the smallest thing we should select. Oh, it looks like a 6. Copy that to the output. All right, an insertion sort says don't do any work when you're selecting what to move. Just move the first thing from the input. Just grab the 10, put it into the output in the correct spot. So output's empty, so we're just going to insert it in the first position. Grab the second thing, that's a 4, insert that into the output in the correct spot. Well, it should go before the 10, so move the 10 down, put the 4 right there. Grab the next thing from the input, that's a 2, insert that into the output. Well, it should go before the 4, so move everything down, put the 2 right there. Take the next thing from the input, that's a 5. Everything should get moved down after the 4, so this becomes 2, 5, 10, 4. Grab the 18, that should go at the end, so you got 2. What did I do here? Grab the 5, so that's a 2, 4, 5, 10. I can sort. Okay, grab the 18, that's going to get inserted at the end. Grab the 6, that should get inserted after the 5. And then grab the 11, that should go in after the 10. And there's our sorted output. And those are all order n squared: bubble sort, selection sort, insertion sort. Basically, they all have this characteristics that we go through our input to do one pass, to copy one thing to the output, right? And we have to do that a total of n times if there's n numbers. So it's n times n, n squared. So those are slow sorting techniques. So merge sort, heap sort, quicksort, those are the faster ones. So let's look at merge sort first. So merge sort, this is where you're interleaving two sorted things to get a bigger sorted thing. So we have two lists. Here's list A and B. And assuming that A and B are sorted to begin with, we can interleave them into an output. And interleaving, we just look at the first thing from each of our sorted lists, and we pick the smallest if we're going smallest to biggest. So pick the smallest of 3 and 4, that's a 3. So now the first thing in each list is 4 and 7, pick the smallest, that's a 4. So now we got a 7 and a 10, smallest is 7. Now we got a 10 and a 15, smallest is 10. Now we got a 12 and a 15, smallest is 12. Now we got a 15 and a 16, smallest is 15. We've got a 16 and a 21. Got a 20 and a 21. We've got a 21 and nothing. And we've got a 25 and nothing. And there's our combined list. So merge sort is really about interleaving two sorted lists to create a bigger sorted list. That's all the work in merge sort. The way we sort an original list of numbers is we split it in half. We merge sort one half, we merge sort the other half, and then we do this interleaving process. So it's recursive, right? So how do we get this list A and this list B? Well, we take our original numbers, we just throw 5 of them over here, and we say merge sort that. Throw 5 over there, say merge sort that, and then do this interleaving process. Okay, and this is a type of algorithm that we call divide and conquer. take your problem, split it into smaller pieces, solve those smaller pieces, and then put the solutions together. And this is classic. And so this tends to be order n log n. Bubble insertion selection, or order n squared, which is n times n, right? So n times log n is better than n times n, because log n is a lot smaller than n usually. So this is a more efficient sort. Heap sort, we'll talk about heaps in a minute, but heap sort is basically take a bunch of numbers, turn them into a heap, and then just keep pulling them off in order. But we'll do that when we get to heaps momentarily. Quicksort is the other one that you should definitely know for the exam. So Quicksort was this business of having a pivot and moving things around. Remember that? So let's make some numbers. I'm going to use the numbers I did last time because they worked out well. A lot of times I have trouble coming up with good random numbers. This is Quicksort. So the idea of Quicksort is we're going to pick one number which we call the pivot, and we're going to go through a process to put the pivot into the correct place in this list, which means we're going to arrange these numbers so everything to the left of the pivot is smaller and everything to the right of the pivot is bigger. And we usually just start with the rightmost thing as our pivot. So we'll mark that as our pivot. So this process we're about to go through is a single pass of Quicksort. Okay, and the purpose is to put the 14 into the right spot in here. So we start by looking at the leftmost element in the list and looking at the rightmost element right before the pivot. And we begin from the left, and we ask, is this number smaller than the pivot? And if it is, then we move on to the next number. Okay, we want everything over here on the left to be smaller than the pivot. So 4 is smaller than 14. Let's move to the 10. 10 is also smaller than 14. Let's move to the 5. That's also smaller. Let's move to the 20. Now there's a problem. 20 is bigger than 14, so we stop. And we move over to the right-hand arrow. And now we're going to move looking for things, making sure that they're bigger than 14. So we check this first number, 11, and that's not bigger than 14, so we stop. So what we found is that these two numbers, 20 and 11, would be better if they were in each other's place. Because 20 is too big and 11 is too small, so we simply swap those two. And now our list of numbers looks like this. So I'm redrawing this, but really all we've done is swap those two numbers, 20 and 11. Okay, now we continue moving our arrows. So move over to the next spot. There's a 50. 50 is bigger than 14, so we stop. We come over to the right. We move over to the 8. 8 is smaller than 14, so we stop. And again, the 50 and the 8 should be in each other's place, so we're going to swap those. So now our numbers look like this. All right, and we continue from the left, so we move over to the 6. 6 is smaller than 14, that's good. Move over to the 50, and at this point we've hit our other set of arrows, so we're done. Okay, so we're moving the arrows. When we find two things out of place, we swap and we continue. when our arrows collide, we're done with this pass. And we have one final adjustment to make, which is to take our pivot and swap it with where our arrows met. So now our list is going to look like this. And I'm going to draw a box around here. And with the box, I'm indicating 14 is in the correct place in the sorted list. When everything is done and I sort all of these numbers, 14 is going to be right here. Now it turns out all these numbers to the left, they're jumbled up. They need to get rearranged. But eventually, they're going to come into order, right? 4, 5, 6, 8, 10, 11, and that's where the 14 will be. All right, so how do we sort this left list?
Do another Quicksort.
Just pass it to Quicksort. How do we sort the right list? Just pass it to Quicksort. So it's another divide and conquer algorithm. Right? In this case, we do a bunch of work in the beginning to get one number in the right spot, and then we take the two pieces on the left and the right of that number and we pass them to Quicksort. And they're smaller than the original list, so eventually we're going to try to Quicksort a list with just one thing, and it's not going to have to do any of this. It'll just return and say it's already sorted. So merge sort, we sort the two halves and then we do some work to interleave. Quicksort, we do some work to basically decide where to split our list, and then we call Quicksort on those two pieces. So it's also generally n log n. It happens to do really badly if your list is sorted to begin with. It goes down to n squared. But in general, it's n log n, just like merge sort.
It's kind of ironic that it does poorly in this.
I know. Doesn't seem fair.
Well, that doesn't really seem to be much of a problem. I mean,
But sometimes, as I said, you actually like randomize your data before you quicksort it, just to make sure. And that's a little weird that like if you jumble up your data, you get better sorting. But that's a life lesson. All right, so I'm not going to ask you to code quicksort or insertion sort or selection sort, but I might ask you to, take a list of numbers, do a quicksort on it like that, or here's a list of numbers. Go ahead and show me, how they get merged together or things like that. So Radix Sort was the one where we were looking at your things you're sorting as a collection of characters. So for example, if you're sorting the numbers 231, 430, 152,
where you look at each digit.
you look at each digit. Right, so we go through and we start with the rightmost digit and we sort these just based on that one digit. Being very careful that if two things have the same digit, we don't rearrange them. So it's got to preserve order. So this would turn into 430, and then 150, and then 231, and then 152. All right, so that's sorted by our rightmost digit. And then we go ahead and we sort based on the next digit. Again, preserving the order if the digits are the same. So 430 would come first, and then 231, and then 150, and 152. And then you sort based on the next digit and preserve the order. So 150, 152, 231, 430, and there's your sorted numbers. You can sort numbers, strings, anything like that. So that's a radix sort. We didn't get to topological sort. I might do that next quarter. So any questions on sorting? All right, so let's talk about heaps. So we've always got two types. We've got a max heap and we've got a min heap. And they function identically with one difference. A max heap, the largest thing is always at the top. A min heap, the smallest thing is always at the top. So I did a max heap last class. Let's do min heaps this class. They're symmetric. So a heap looks like a tree. It's not a binary search tree. There's no rule about left child versus right child. Okay, left child could be larger, it could be smaller. The only rule, if we have a min heap, is it has to satisfy the heap property. So what's the heap property for a min heap? Do you remember?
The parent node is smaller than its children.
Parent node has to be smaller than its children.
I thought that was for a max heap.
For a max heap, it's got to be larger than its children. And that's the only distinction between a max heap and a min heap, is what that heap property says. So every node in the min heap has to be smaller than its children. And the heap has to be in the shape of a heap. So the heap shape means that every row is filled in down to the bottom row, and the bottom row has to be filled in from left to right. So that's the heap shape. If I throw another node over here, that's no longer satisfying the heap shape. Because before I put this in, I should have also put this in, and I should have put that in. So now that's satisfying. And that conforms to the heap shape, right? So a heap is something where every node satisfies the heap property, and the whole tree is shaped like a heap. So every layer except the bottom is filled in. The bottom's filled in from left to right. All right, so there's like 3 things I think you need to know about working with heaps. Removing, inserting, and heapifying. Okay, heapifying is separate, so let's just talk about inserting and removing. So let me make you an arbitrary min heap. I feel like I'm going to mess this up because I'm used to doing max heaps. So is that a min heap? No. Is that a min heap? Okay, good. I knew I was going to mess up. All right, so that's a min heap. Every node is smaller than its children, and every layer except the bottom is filled in, and the bottom one is filled in from left to right. Okay, so 2 main operations, removal and insertion. Okay, removal, you always remove the root. The root's always the smallest thing in the heap, and we always want to remove the smallest thing. So to remove, we just grab the root. So we'd pull off the 20. And then we got to replace it with something, because we need a root to the tree. And the only thing we can really move is this last thing on the bottom row. If we tried to move the 59 or the 55, it wouldn't look like a heap anymore. So when you remove the root, you take the last thing on the last row and you put that up to take the place of the root. And it's probably not a heap anymore because the things down here are usually really big and the things up here are very small. So we have to turn it into a heap again, so we do this thing called down heaping. And down heaping basically says, see if you're satisfying the heap property at this point. And if you're not, what do we do?
I'd say vacation, but I think that's wrong.
That's too powerful. So we moved to 158 here, yeah, down heap, right? So we move to 158 here, so see if it violates the heap property. If it does, down heap, which means swap with the smallest child. So smallest child is 30, so put a 30 up here, bring the 158 here. And then see if that satisfies the heap property. It doesn't, so we need to down heap again, swap with the smallest child. If we swap, sorry, with the largest child. So put the 37 up there.
Where's the largest child then?
Oh, min heap. 35, 158. And this is still 37. All right, and then 158 has no children, so it satisfies the heap property. So to delete, we grab the root, we replace it with the last element, and then we down heap. So now our heap looks like this. And to insert, we basically do the opposite. So insert, we always put our new element in the next position in the heap. So let's insert 5. And then we upheap. So we look at this node's parent and see if it satisfies the heap property. It doesn't, so swap with the smallest child. And now look at that node's parent, 40, see if that satisfies the heap property. It doesn't, so swap with the smallest child. And look at that node's parent, 30, see if that satisfies the heap property. It still doesn't, so swap with the smallest child. And that node has no parents, so we're done, and we've got a heap again. So remove, pull out the root, replace with the last child, down heap. Insert in the last position in the heap, and upheap. And that's true for max heaps or min heaps. Okay, but the definition of upheap changes. Right, well, upheap means see if you satisfy the heap property. And then if not, swap with either the largest or the smallest child, depending on whether it's a max heap or a min heap. Okay, so those are two things you want to know how to do with heaps. Remove the root element or insert a new element. The third thing is heapification, and heapification is different. Okay, heapification answers the question, suppose you have a bunch of numbers, how do we build a heap out of them? And instead of inserting them one at a time the way we just described, when we heapify, we do the following. We take our numbers and we simply put them into a heap shape. So let's say that's the order our numbers came in. We just lay them out going down each row. And there's an ordering associated with these. We think of this as the last element in the heap, this 7. This is the prior element, this is the prior, and so on, and 4 is sort of the first. So to heapify, to turn this into a heap, we simply begin with the last element, and we check its heap property. So is it smaller than both children? Yeah, it has no children, so this node is fine. Move to the next element, 11, that has no children, so it's fine. Move to the 5, no children is fine, 6 is fine, 3 is fine. Move on to the 2, is 2 smaller than both children? Yes, so that's fine. Move on to the 1, is 1 smaller than both children? Yes. Move on to the 10, is 10 smaller than both children? No. So here we have to adjust, so we're going to swap with the smallest child. And now, check if this satisfies the heap property. Is 10 smaller than both children? No. So swap with the smallest child. And we get that. And then move to the next node, which is just the root, see if that satisfies the heap property. It doesn't. Swap with the smallest child. Does that satisfy the heap property? Yes. And you're done. And
So let's see, we do it from right to left?
So you start off with this one and you keep going like that.
When you swap the 10 with the 3?
I wanted to swap with the smallest child.
Oh, smallest child.
Yeah, because it's a min heap. Right, so there's a min heap, and it's got the heap shape, and it's efficient to do this. This is n log n. If you swap with the wrong child, you end up not satisfying the heap property, so it'll jump out at you immediately. Right, so if I'm doing a min heap, and I have a 10, and a 5, and a 3, and I accidentally swap the 10 with a 5, right, I can tell I did something wrong because this also doesn't satisfy the heap property. Right, so I should have swapped it with the 3. Alright, so that's what we mean by heapifying. It's turning a bunch of numbers into a heap. All right, that's pretty much the most important parts of what we've been talking about this quarter. We already talked about the exam in general, right? So 4 or 5 programming questions, and then 5 questions where you're doing things like, here's a bunch of numbers, show me each step of a quicksort. Or here's a bunch of numbers, put them in the shape of a heap and heapify. Or things like that. Here's a tree, insert a number, and rotate it to make it balanced. So things you've done as practice on the board. So any other questions? Yeah?
Right, trying to manipulate the structure.
Oh, that's everything we've done this quarter. That's a real catch-all statement. So if you write code that inserts a node into a linked list, right, you're manipulating a structure basically, because a linked list is a data structure. So that's kind of the one-sentence synopsis of CSE 222, I guess. I don't have any short answer, fill in the blank kind of questions on here, so these things that say discuss GDB or Valgrind don't really apply, but they're good to be able to do anyway. Any other questions on the exam for 222? All right, we got 6.5 minutes. Let me teach you Java in 6 minutes.
Now there's
Yeah, you'll be glad you came to class today. So no, let me just give you a teaser for 223. So how many people here have done anything in any kind of object-oriented language?
I'm currently working with Python.
Okay, cool. So it's more and more common that we bump into this. How many people have played with an Arduino processor to like blink LEDs or anything like that, right? The language you use in there is object-oriented, but it looks like you're using C, right, with some extra bells and whistles. You can create a servo, and you can say something like, servo. Do you know what a servo is? It's like a motor. You can control the position that something turns. So you can say, okay, give me a servo called S, and you can say S.set position 90 degrees. And if you've got it hooked up to pins on the Arduino, the little thing inside will turn to 90 degrees. And if you say S.set position 180, it'll turn to 180 degrees. Well, this is object-oriented code, right? Servo is a type of variable. It's like a structure statement in C. So when we say servo S, there's things about this. There's fields we can get to in S. But we can get to this thing that looks like a field, but is actually a function. This thing called set position. And it's part of this structure. So in C, in this course, we created structures and we had something like a struct T node. Let me just call it a node. And it had a piece of data, and it had pointers that we called left and right. Okay, so we build a tree out of these things, and in my main program I say something like struct node my tree, and I do some mallocs or whatever, right? Well, one of the things we like to do with my tree is figure out its height, right? So I have a function called height, and I say, you know, print height of my tree. And you've done this, right? It was in your PA4. Well, here's the thing. This function height, the only time I'm ever going to use this function is when I'm trying to find the height of a tree. The only thing I'm ever going to pass to this is a pointer to a struct node where that pointer represents the root of a tree. It's not like a square root function that I might use in a bunch of different places. Really, the only time I'm going to use height is when I'm talking about a tree. So imagine that our struct node, which contains, you know, a piece of data and pointers to left and right children, imagine if we also included in the structure a function called height. So instead of just being a function that, you know, anybody can call from anywhere, this function is now a piece of this structure, just like the data is. And this is a little bit like information hiding, right? When we have a tree, we don't really want the user doing things monkeying around with the left and the right pointers. We want the user to say, here's my tree, add a number to it, delete a number, tell me if this number is contained in there. We don't really want the user saying, tell me what's to the left of the right subtree of the root, right? Because that's monkeying with our implementation. So same thing with height. Let's make height a piece of the structure. And now when I want to find the data of the tree, right, I could say something like my tree, and I'm switching to pseudocode here, right? So I'm just going to use a dot instead of an arrow, right? I can say mytree.data to see the root value. I can also say mytree.height. And when I say this, the system is going to run the height code on whatever my tree is. And this is going to return the height of my tree. And if I want to know if my tree is balanced, I could say if my tree dot is balanced equals 1. And this is just extending the idea of a structure to also include functions as well as pieces of data. Right? The reason we use structures is because when you have an integer called weight and an integer called value and a string called name in PA5, all of those three things belong together. Right? We don't really care about just this arbitrary thing called weight. We care about the weight and the value and the name. So we put them together in a structure called item. And if we want a bunch of these things, we can make an array of items, and I can pass that array to my print routine, and it can go through and grab each element, which is an item, and that item has a weight and a value and a name. Well, suppose I have something else, like suppose I'm writing a greedy algorithm and I want to be able to calculate what's the value per weight of this item. So I might write a piece of code that does that calculation. Well, that code could be part of the item structure also. Yes, so that's exactly what we're talking about. So these are called classes in Java, but it's like a structure. But in addition to having data, it can also have code. And that's sort of a central idea of an object-oriented language. So these things are generically called objects, right? And a description of them is a class instead of a struct. So different keywords, but basically it's just an extension of what we've already been doing with structures. And Java looks a lot like C. The syntax, the statements, the semicolons at the end, the curly brackets, all of that's going to be the same from C. So you can write C in Java, right? But that's not really the goal, because you may as well use C. But you can take what you know about C and use that and add in what we're going to learn about putting code into these structures, right? These classes. And that'll get us into object-oriented programming. And after a few weeks of doing this, it'll feel completely natural. And working in something that's not object-oriented will feel kind of like this is missing something. So it'll get really comfortable, and we can have a lot of fun with it, because once we're in this framework, we can start using all these classes that have been built for us to do things like make GUIs or work with more complex data structures and so on. Yeah, yeah.
I would find it more enjoyable if I understood how object-oriented it works in terms of Python Arcade.
Ah, we could dig into that.
Yeah.
All right. So there you go. So I will see you if you're in 2:15 in a half hour. Otherwise, have a great weekend, and I will see you in your exam.